How we doing today, AP Statistics? We're going to be starting off our lesson with an example, identifying association and defining correlation. Okay, so we're talking about association, and when we fit a number to that association, that's called correlation. So for the set of data below, determine if there is a correlation between almond and pistachio prices by step 1. We're going to make a scatter plot. We're going to let X be the almonds and Y be the pistachios. So our X-axis value is going to refer to the price of almonds and Y is going to refer to the price of pistachios. And then we're going to make sure the scatter plot indicates the three conditions for correlation are upheld. That is quantitative data. The data need to be quantitative. Well, check. Linear pattern, we're looking for that, and also no clear outliers. So we're going to go to the calculator and we're going to put this information in and see if we can find a linear pattern with no clear outliers in our scatter plot. Let's do it. So here we are at the calculator. We're about to generate a scatter plot. What I'm going to do is I'm going to go to second. We're going to go to stat plot. As you could see, I've already input my data. I'm going to go to plot on, make sure the plot is on. It appears to be set to scatter plot already. Very good. Pardon the glitchiness there. I'm going to go to zoom. We're going to go to zoom number 9. Let's check it out. That's pretty linear. And there are no real outliers. Yes, this fella does break from the mold. But honestly, everybody seems to be behaving, as it were. So there are no clear outliers, and I do see a linear pattern. That is awesome. Back to the slide. Now we are going to go to step 3, which is compute the correlation using linreg. There are a couple of features in the calculator that start with linreg. That's short for linear regression. We'll talk about what that means in the next section in great detail. Right now, all you need to know is put a line of best fit to it and do a little analysis. Part of that analysis is fitting a number to the association that we call the correlation. We're going to see what that number is and analyze it in terms of strength and direction. So any of the linreg family will do. One thing we do need to make sure of is that diagnostic is turned on. That is very likely the case already, but just in case it's not, we're going to handle that first, and then we're going to use my favorite of the linreg family, which is linreg t-test. We're not going to know the full significance of linreg t-test until literally the last chapter of the year in our textbook, but we're going to start looking at linreg t-test and all the wonderful things it has to offer in this section. And we're back at the calculator. So what I'm going to do first is make sure that diagnostic is turned to on. So I'm going to go to second, and above 0 is catalog. All right. This gives an exhaustive list of all the fun features that your calculator can do. So I'm going to use the little alphabet feature. You'll see that there are little green letters. It's not just for leaving messages for your friends to find and decode. It's to use for actual calculator purposes. So I'm going to use this little green letter D to skip all the way to D is for diagnostic. And we're going to go to diagnostic on, right? We click and it says done, which means that we are able to use the linreg family, okay? Probably was already set to on in your calculator, but just in case, we'll make sure diagnostic is set to on. Now I'm going to go to linreg t-test. To get there, we're going to need to go to stat. We're going to click stat. That's usually the world of edit, but I'm going to go to this interesting world you probably have never been to called tests, all right? We will spend a gargantuan amount of time this year in the world of tests, all right? Also, we'll spend a lot of time in the world of calc. However, tests does take the cake for our most often visited feature at the end of the year, with the possible exception of edit, but we spend a lot of time in tests, believe you me. All right, so we're going to go near to the bottom, and we're going to find linreg t-test. I mentioned that one before. Let's go to linreg t-test. It's going to ask us for a few things. X list is list 1. That's our almonds. Y list is list 2, which is going to be pistachios. And frequency, don't worry about that. Greek letters beta and rho, don't worry about that. You'll learn about that in chapter 26. Beta specifically. Regression equation, don't bother with it. Just go straight on down and calculate. And we hit enter. And we get a lot of information that we do not need. What is beta? What is rho? What is t? What is p? What is df? You'll learn what all those mean later on. But this is computing something called a regression equation. You'll learn more about that in Chapter 7. But in addition to that, it gives us some information that is important to us. That's a familiar character. That's called the correlation coefficient. You know about that. And here is something called variation accounted for. So R and R squared are closely related. And we'll talk about the full implications of that later on. But let's look at R right here. The correlation is about 98%, all right, so 0.978. That is a positive number, so the correlation is positive, and it is a strong correlation because it is very close to 1. Okay, so it is a strong positive correlation like we saw in our scatter plot. We're basically confirming mathematically what we saw. So now that we've found a correlation coefficient, we're going to talk about properties and a couple of the fine details, a bit of nuance about correlation in general. R, the correlation coefficient, the numerical measurement for association, is between -1 and 1. -1 being perfect negative correlation, the answer marching 1 by 1 down and to the right, and 1, perfect positive correlation, the answer marching 1 by 1, perfect straight line up and to the right. Real world data do not have an R of -1 and 1. That is what contrived data would look like, run from these data. However, technically R can be between -1 and 1. R doesn't change if the X and Y variables are reversed. May seem a little strange. Think about it. If we were to flip the graph on the prior slide, the graph that we got from the prior slide, in which the almonds were on the x-axis and the pistachios are on the y, yeah, the graph would look different, but it would still be just as linear. And the correlation would still be positive, right? So the correlation is not going to change if we flip the x and y values. The strength and direction are going to remain the same. R has no units. Sometimes it is represented as a percentage, but it technically does not have any units. And I'll let you think about why that's true. Consider how we get R. You might want to look at the prior video if you're curious. R is not affected by changing the center or scale of data. So if we perform one of those data transformations that we've talked about before, R is totally unaffected, okay? That's pretty neat, okay? We can change the center of the data and the scale of the data, and we're not going to affect this measurement of association that we call correlation. There is not a meaningful cutoff separating a strong from a weak correlation, and that is intentional. We'll talk about this a little more in the next section, but there's not a cutoff that says, okay, past this point, a correlation is strong. Prior to this point, the correlation is weak. It's a little too close to a correlation of 0. It's weak. It's very close, or this close or that close to 1 or -1. It has to be strong. No, there's no cutoff, and that's intentional. The reason is because for certain instances, you need a value for R that is exceedingly close to 1 for your data to be taken seriously. We're talking about research in chemistry, research in physics, hard sciences like that. But if you're doing a study in, say, sociology, if you're doing a study in psychology, and you can establish a trend with an R value that's like not even close to 1, like we're talking like 0.5, 0.4, 0.3, something like that. If there's like any sense of direction in your data, those values for R that I just gave in some cases are unbelievably good numbers, okay? And that is strong enough correlation to demonstrate a result in some of those soft sciences, like I mentioned. So it really just depends on what you're studying. There's no hard and fast cutoff for this is good correlation, this is bad correlation. Now we get to talk about something almost a little humorous. This is accidental correlation. Even data that should not have a meaningful association, there's no reason to think variables are related, has some correlation. If you were to make a scatter plot, it's going to have some kind of trend, but that is by accident. This is a scatter plot over here of the age and height of each player on the roster of the 2017 Cincinnati Reds, which has a correlation of 0.221. Now, this number is not 0. So, though it is weak, there is a positive correlation. But consider the variables. We have on the x-axis age and on the y-axis height. Now, these are all adult men. What does the variable age have to do with height? These are all people college age and up. They are, for all intents and purposes, done growing or very close to being done growing. There really shouldn't be an association here. So though this number is not 0, we shouldn't say, oh my goodness, there's some kind of positive association between age and height among Major League Baseball players who are in their 20s and up. That doesn't make sense. There is correlation, but we shouldn't take it seriously. So we have some more pitfalls of correlation. Assuming correlation means causation. A strong correlation between variables does not necessarily imply causation. I'm going to say that again. A strong correlation between variables doesn't necessarily imply causation unless the study in question is a well-conducted experiment. That is a technical term, experiment. An experimental study is something we'll talk about in Chapter 12. It's one of two types of studies, the other being observational. Okay? So unless you are conducting an experiment, you cannot conclude that a correlation, even a strong one, implies one variable causes another. Okay? More on that in Chapter 12 about the experiment. So, in an observational study being we simply observe variables interacting, things happening, and we collect data on those variables and we see if there's a trend. We could run into something called a lurking variable, all right? Or rather, not run into something called a lurking variable. It's a variable that is not being studied that is actually responsible for an apparent relationship. Well, let's look at this graph right here, this ridiculous graph. We have number of pirates on the x-axis, approximate, LOL, and global average temperature in degrees Celsius. At least they use SI units. And we see that as the number of pirates goes down, then the global average temperature goes up. So I guess that means we have to become pirates if we want the global average temperature to stop going up. Well, that's obviously not the case. There's a lurking variable involved. We may observe that the number of pirates does in fact correlate, and strongly so, with the global average temperature. Even though this x-axis is problematic for multiple reasons, we may find a strong correlation. The issue is that does not mean that the number of pirates has any effect on the global average temperature. There's a lurking variable, and there could be many lurking variables. Geological things, man-made things, things that may increase the temperature over time. All right, so any one of those things could be a lurking variable. We should not don our pirate gear if we want to lower global average temperatures. That is very silly. This is an example that I like. This is from the textbook. Suppose there were a strong positive, there were a strong positive correlation between the number of firefighters at the site of a house fire and the amount of damage at the house. Surely it's not the firefighter's fault. Well, duh. What could the lurking variable be? Well, we don't want to assume as the number of firefighters increase, they're causing the damage. That's kind of ridiculous. What's the lurking variable? The firefighters are not causing the damage. The size of the fire is causing the damage. And the bigger the fire, the more firefighters are going to be summoned. So our lurking variable here is size of the fire. We can't assume firefighters are destroying the house. That is literally the opposite of their job. It's the size of the fire that is causing this association to happen. And I can assure you there is a very strong correlation between completing this assignment and improving your grade. So I recommend you do it. Have a great day.